So, last class, we didn't really continue PLCs, but we did talk about proximity sensors. All right. And those were all non-contact. All right. So we talked about what were our options? We had the ones that used like the thing coming out up here. Light. We also talked about ones that could use sound. All right, excellent. And then we did the sensor that we actually wired up in class, which only detected what? Metal, that's the word I'm looking for. All right. So it wasn't actually touch. If you notice, when you got close to it, it triggered, not when you actually touched it. All right. But it only detected metal. So like you put your hand there all day long, won't do anything. But if you use metal over it, that's ferrous, all right, and it would detect that. All right. So, but we talked about all those different types of lovely proximity sensors. We also talked about transistors and how they work. All right. So, quick review. Today we're going to move into the other world of PLCs. All right. Or the other world of sensors for PLCs, which is the wonderful world of analog, which again we've talked about ever so slightly. So first, if this will listen, is the wonderful world of discrete. All right, hey, go back. Where's my pen? All right, so discrete would be the sensors that we've been dealing with, whether it's an actual physical button you're touching or those proximity sensors. Those are discrete. They are on or they are off. All right, there is no other state. You may hear someone refer to those as digital inputs. All right, and I am one of those people. I call them a digital input. It's a signal. Digital is traditionally, in my mind, zeros and ones. But I feel like in the world of PLC, if someone talks about a digital input, it's more of like a networking port or something, like serial or CAN bus, Modbus, something like that, where it's it's pulses. So it'd be something like that. That'd be a digital input. Where we're dealing with discrete, which is just pulses like that, but just depending on the button being pressed. All right, so to me, not a lot of differences there. And as I said, discrete is probably the most used input that's going to be on your PLC. All right, now that leads us to analog. All right, and if a discrete is a 0 or a 1, what is analog? All right, you say -5 to +5. You're thinking of networking signals like RS-232.
Well, like there.
Okay, so that'd be what, like 0 to what?
Well, no.
It goes into the negatives? No.
Sir.
Yeah. All right. AC does go negative. Yes. All right. Analog is going to be a variable. All right. So it doesn't have to be a 0 or a 1. There's only two states there. This should be like say 0 to 255. All right. Or 0 to 512 or something like that. And anyone know how we determine what number this is? All right. That is going to be based on the number of bits that your device has. All right. So that is going to be it. So analog, didn't mean to go there. So it's variable. So we have this signal that goes from 0 to some number. And that some number is all depending on how good of a analog to digital converter, the ADC, analog to digital converter. All right. You also have a DAC. What do you think that one is? There we go, digital to analog. Right. So if we let me quick erase my screen. So if we just had a plot, come on, go. That would be an analog signal if we gathered it every millisecond over time or whatever the case would be. All right. So that would be what our analog signal would look. That could be temperature, it could be pressure, it could be light, it could be thousands of other things. Right? But that is our actual temperature graph. Now again, our PLC is going to convert that from a voltage signal or a current signal. So how do we send this signal to the PLC? Well, our sensor has to have a little bit of smarts to it. Right? Not necessarily, I guess. But like there are what they call your standard like temperature sensor. All right. most of these analog sensors are going to have a little bit of smarts to them, right? Which means we're going to have 3 wires. You're going to have a positive, a negative, and a signal, right? So the sensor itself is going to be powered. A lot of these, like temperature and pressure and things like that, they're going to be based on what's called MEMS, which are microelectric mechanical systems, which are infinitely small systems that, like, when pressure is applied, it physically adjusts the capacitance of a capacitor by moving the plate internally. Like, it's that freaking small. It's how your phone does, like, compass and acceleration and things like that. It's actually a little mechanical device inside your phone that's micro freaking scopic. All right. But that's how we're doing this. All right. So, and then it takes that and says, okay, I'm going to send this out. How it sends it out is one of 2 options. We either have a voltage option or a current option. So if we're going to use the wonderful world of voltage, all right, we have either 0 to 10 volts, or actually you might also see negative 10 to 10. All right, so that also could be a possible voltage. All right. However, we don't actually like using voltage as our signal. Is it an option? Yes. Are there sensors out there that use it? Yes. Would you possibly see it in the real world? Yes. But that's not the best option. And the reason being is electrical noise. All right, again, industrial environments are stupid noisy when it comes to electrical things. All right. So having a power turn on and off or something next to a temperature sensor, a voltage analog signal could cause a spike in that, which could cause your readings to get all skewed. All right. So that is something that we definitely need to take into account. So what we prefer is the current. So this is the preferred option. It's a current system. All right. So this is either 0, 20 milliamps, or 4 to 20 milliamps. Now I'm like 95% sure I've asked this question before. Why do we have 2 ranges? Like, if I were you, I'd be like 4 milliamps. Why are we starting at 4? That's wasting 4 milliamps. That's 1/5 our range. Why do we want to waste all that range? Pretty sure I've asked this question. Nope. It's for dead sensor detection. Yeah. So you're like, oh, he did say that before. So if I always have a minimum of 4 milliamps that I'm sending out as a signal, my PLC knows the sensor is there, and it is taking a reading. Right? If I send 0 milliamps, the PLC says, well, either the sensor's not there or it's disconnected. Or the sensor is there and it's not, it's sending out 0 milliamps, or it's disconnected. All right, so either of those are a possibility. All right, so it is definitely something that you need to be aware of. So this is why, as far as I'm concerned, the 4 to 20 milliamp is your best option. All right. Yes, you lose range, you lose useful accuracy, but it gains you known detection of your sensor beam. All right. It's almost like every button and limit switch and whatnot should be normally closed, because that means when it, well, maybe not. Yeah, no, it doesn't really make any difference. Ignore my last statement recording, people. Yeah. All right. Yeah. So 4 to 20 milliamp is the best option. All right. All this is a voltage measurement with a high precision resistor. So inside your device, you're gonna have a resistor there that you know the value of. It's like if you guys are all in 110, hopefully, or you're taking it. It's like, okay, you've got a resistor that's 100K plus or minus 5%. That ain't gonna cut it here. You need to know that it is 5K or 5 ohms or whatever the magic number is. So that way, when you have a resistor and you say there's 40 milliamps, or well, let's go with 10 milliamps flowing through it, and this resistor value is, we'll say 5 ohms, you can do V equals IR, and you can say, okay, we're going to measure the voltage here. And we're going to put my voltmeter there. And I know there's 5 ohms of resistance, and I know the voltage is this. I can now calculate the current. So we actually can still do it with a voltage measurement. It's really nice. All right. So, but that's only works if we know very accurately the value of that resistance. So that is something that we need to take into account. Now, I do have some examples. I've already told you temperature, light, pressure. You also could have distance sensors. So you could have a sensor on a conveyor belt that says the box is 5 feet away, the box is 4 feet, 3 feet, 2 feet, those types of things. Right? You also have level sensors for tanks. So how full is that tank of water? All right. So just some examples. And the last thing on this screen that I want to talk about are analog comparators. All right. And right here on the right is an analog comparator. Now, this is something that we actually have over there in our little assembly line. And when I research analog and comparators industrial, I actually don't get many hits. So I don't know if this is actually something that is used in the world of industry, or this is just like, something that Festo created for our little simulated PLC line over there. But most of the time, you're going to take those analog sensors and you're going to feed them right to a PLC. The PLC just requires an analog input to take advantage of that then. Right? If your PLC doesn't, well, then you would add an analog module, like I showed you guys the other day when we were talking about PLCs. I had those that you could just plug on the front. All right, that happened to be ours that worked. Or you could do something like this, which is an analog comparator. So as you can see here, we got 24 volts and positive and negative there. You've got your analog in and a positive 10 volt signal here. And then up here at the top, you have ground. And then if you notice, you have 3 other trigger signals. All right. And this would be level 1. This would be the ideal, called I, and this would be level 2. And what you do is you'd say, this is the analog, this is the pressure I want. So you would like set the pressure in the tank or whatever to that pressure. And then you would adjust these dials up and down until you have only in that, when you're in that specific range that you're acceptable, the green light would turn on right here, which would then turn this output on. But when you're not, if it's too low, it will turn this one on. If it's too high, it would turn this one on. All right, so you could actually tell that with 3 inputs on your PLC if you didn't have a whole analog input option. Okay, so that is a great little option there for you. Okay, so any major questions on analog at this moment? All right, we're going to quick watch a real parts video on analog just to kind of bring it all together for us. So just a kind of a quick review of analog. They did get into the thermocouples and whatnot, which are a whole different ballgame. Right? And if you ever do get neural thermocouples, make sure you're stay consistent with your equipment. So like they said at type J, there's also I think type K and a whole bunch of other ones. So like if you have a probe that can read type J thermocouple and you put type K in, it's not going to work. So whatever your test equipment can handle, make sure that that's the sensors that you're using. So they have different ranges and different capabilities. There's so many weird tweaks to thermocouples like that. So, and you would think it's just analog measurement, right? All right. So again, remember I talked about being pseudo smart. Yeah, okay, you could have an analog sensor that takes a thermocouple input and still outputs a 0 to 10 volt or 4 to 20 milliamp signal. A little bit of give and take going on there. All right. Yeah, so here we have our ADCs and our DACs. All right. And this to me is actually very interesting. All right. This one now. Bring up notes. So we've talked about bits already. All right, and this is the resolution of your analog to digital converter or your digital analog converter. So if we have an 8-bit, nope, don't have a pen. If we have an 8-bit, that would be 256 steps. If we had a 10-bit, that'd be a 1024. All right. If we had 11 or 11, that'd be 2048. And it just keeps going up from there. Now you may be going, if they all only measure to 10 volts. We're just going to go with 0 to 10 volts here just to keep life simple. Why does it matter? All right. And then why it matters is if this is my 10 volt point, 0 volts and 10 volts, right? If I only had 10 steps here, there we go. Ends up here. All right. You would only be able to read in 1 volt increments. So even if that sensor is now putting a 0 to 10 volt signal and it's analog, it could be anywhere between 0 and 10 volts. It could be 8.362 volts. You're only going to be able to read whether it's 8 or 9 volts in that case. And you would probably write, oh, that's 8 volts. All right. So that's not giving you a lot of resolution, giving you 8 steps. Now, if we said we had 1,000 steps in there, all of a sudden, instead of being able to read 1 volt, we can read better than 1/10 of a volt. We can read 1/100th of a volt. So you would now be able to read down to 0.01 volts with 1,000 steps there. All right. So that now gives us much higher accuracy, which is kind of what they're showing you here. It's like, oh, if you want to be able to read this point right here, well, this system won't do that. It'll read close to it. All right. This is also why when it comes to analog, you have to be very careful about writing your logic, because you can be like, when it equals 83.4 degrees Fahrenheit, and you're like, you're based on your temperature sensor and your accuracy and everything, it will never read 83.4. It'll read greater than 83.4 or less than 83.4, but it will never be exactly 83.4. So you have to be very careful about your logic to make sure you're doing more like greater than or equal to or less than or equal to types of things instead of specifically equal to, because that will bite you in the butt there. So, but yeah, so the number of steps is going to be very, very important. All right. And so there's also, let's say we need to read, again, 83.4 degrees. Well, if we had a thermocouple or a temperature sensor that could read between 0 and 1,000 degrees, and again, we only have 1,000 steps, we're still only accurate down to 1 degree. But if we have a temperature sensor that only reads between 80 and 90 degrees, and we have 1,000 bits, that's 10 degrees over 1,000 bits. We have lots of accuracy. Right? So not only is the resolution of your analog to digital converter important, so is the resolution of your temperatures. All right. So there's a lot of games that you have to play when you're picking analog sensor. It's not just, oh yeah, give me an analog sensor, that's my range is within, that's perfectly fine. Like, well, it might get you close, but it's close enough. Depending on your situation, maybe not. Maybe you're heat treating something and you need to get it to a very specific temperature, so it's a specific hardness. You don't want to go too hot, your resolution could screw you up on that. So you do have to be very careful about that. All right. We also have PWM. Anyone know what PWM stands for? That would be pulse width modulation. All right. So oftentimes when we are dealing with analog signals from a digital world, we're not actually sending true analog values out. All right. What we're doing is we're pulsing an output to make it look like it's that analog signal. All right. So let's say we're in the world of PLCs here, right? We're sending out 24 volts out of our output. And we got 24 volts here. If I were to turn my output on, where's my mouse? That one. If I were to turn my output on, right, and I took a voltmeter reading of that, it would be 24 volts, right? Now, what if I had it on and then off for equal amounts of time? And you took a volt meter, what do you think you would read? Well, depending on when you're reading it, right? If you read it while it was on, it'd be 24 volts. If you read it while it was off, it would be 0 volts. Now, imagine you did that for a millisecond on and a millisecond off. 1 mil on, 1 mil off, 1 mil on, 1 mil off, 1 mil on, 1 mil off. All right? That's like you slamming the gas pedal, letting go of the gas pedal. Slamming the gas pedal, letting go of the gas pedal. Right? You're never going to get to full speed in your car, right? You're probably only going to get to half speed because you're only on the gas pedal half the time. So if you average, because that's how most things would kind of see this, they're saying full power, no power, full power, no power, you would now see 12 volts. So depending on how long the on time is compared to the overall time, or total time, you would get an average. And that's what pulse width modulation is doing. So you're like, hey, I need 1 volt from 24 volts. It would be on for 1/24 of the time and off for 23/24 of the time. All right, so we can actually turn it on and off really quickly. Now, a lot of PLCs, you might need specialty hardware to do this. All right, like our relays aren't going to click fast enough to do this well. All right, you need solid state transition outputs for this to be able to transition fast enough to get that type of thing. If you're even trying to play that game, it's probably not the right game to be trying to play with PLC. You want to buy an analog to digital converter or digital analog converter to actually do this, so we don't have to worry about that pulsing thing. All right, so a lot of games that can be played there. Now, all this analog stuff takes us to the wonderful world of Hart. All right. And just like I meant to do with the analog, we're going to watch a video, except for this time we're going to watch the video first. So if 12 is the middle, we're only going to 20. Or, I mean, if we're only going to 20, why is 12 the middle? We would think it'd be 10, right? But where are we starting? 4. 4 to 12 is 8. 12 to 20 is 8. All right, so because we're not starting at 0, 10 is not the middle point. So is Hart a network? This is a networking class. So is Hart a network? I mean, I hope so. If we're talking about it, I hope it has to relate to networking somehow, right? Okay. So yes, I would actually say that Hart is a network because especially if you look at this image, right? You have multiple devices all sharing 2 wires for communication purposes. In that instance, if you think about it that way, yes, it is definitely a network. We are sending data, multiple types of data, which I think this video is about to get to, over the same 2 wires. All right, so yes, I would say Hart is a network. All right, we're doing kind of obvious since we're talking about it, but you know, a little give and take. We did talk about PLCs for like 2 weeks. So that's really important there. All right, what did he just say? Yep, we're all sleeping, playing on our phones. All right, Braden's. All right, so basically, when we are superimposing the signal, you may be thinking you're changing the signal, right? And the answer is yes, you are technically changing the signal, but you're changing it in both directions at the same time, right? But if I just drew through here, oh, I gotta hit this button. I just drew through here. All right, basically what he's saying is, as this comes up and whatnot, everything is equaling out. Right? We have just as much above as we do below. Now this picture doesn't quite show that, in my opinion, but that's what they're trying to get across to you. So again, we just talked about pulse width modulation and how we're averaging it. Well, the same thing is happening here. We're averaging. We're 1200 hertz. Right? That's 1200 times per second. This is going up and down. Right? So because of that, we are averaging out back to null zero. So whatever the carrier voltage is, all right, which is going to be somewhere between 0 and 24, I think, or 48, depending on the signal type. I don't know what these are, but we're doing 420 milliamp signals. But what are the voltages? It's not averaging over anything. We're not changing it at all. All right. So yes, in that exact moment, if we took a specific reading instantaneously, yes, we would see a difference. But since we're averaging these readings, because we're not reading instantly at every freaking millisecond, we're averaging it out, we can see that. We don't see the signal at all. It's just like the signal doesn't exist unless you are specifically looking for the signal. All right. As you just said, like with how many of you guys had caller ID at home on your old house phone? Anybody? Yeah. You're youngins. I remember having to dial out the AOL to get on, not just pull your phone out and get on the Wi-Fi. All right, but anyway, so yeah, so like you didn't know there was caller ID or anything happening in the background, so it was really convenient in that aspect that it was just there. Now, what always amused me is if you want a caller ID on your phone, you had to have your phone have batteries in it to accept the caller ID. Your phone did not need batteries to answer the phone call. But it did need batteries to show you the caller ID. You needed power for that. It had to process that information. Where the actual phone call was, again, being powered over the phone line. Kind of an interesting little tidbit there. All right, I just wanted to come back to this because we were just talking about it. And how it's like, remember how I said this doesn't look like it's averaging out? Well, this one's not averaging. They're saying, and this is 100% my opinion on real powers, they screwed this up. All right, but if they're saying 120 hertz, all right, where does that measure from? We're talking about an AC sine wave. All right, what's coming out of the wall? I say it's 60 hertz, right? That's what we have coming out of the wall. Where does that measure from and to? there's our 0 line, right? It measures from the point it starts to that point where it would repeat again, which in our case would be all the way out here. All right. Is this so if we were measuring this one, it would go from here to here, right? So we actually got like 1.5 periods on this graph, and it's the same way for both. Like that's 1.5, and then this one would be here to there to there to there. So again, we've got 1, 2, 3.5 pulses here. All right, so they were showing this for good visual, but I think it was a little misleading in that aspect where it's like, oh yeah, this is evening out. It's like this picture is not even at all. So I just wanted to point that out to you guys that I think they kind of screwed that one up just a little bit. Not a whole lot, but they did mess it up a little bit. All right. So let's go ahead and quick go through my little video, what I got here. All right, so we already, this video talked about Hart is what we're talking about here. All right, and that is highway addressable remote transducer. All right, and this does say that they are smart. All right, remember I said that analog is semi-smart. All right, this is actually smart because we are sending digital data. We have to have more information. We have to be somewhat smart to be able to say, yeah, here's an analog value as well as all this other information. So we need to have some way to process that. All right, and we can control these sensors in all sorts of ways, which is very, very convenient if you ask me. All right, and this is a hybrid, right? We're dealing with an old analog system, which is 4 to 20 milliamps, and then we're adding a digital system basically on top of that. So it is a hybrid system. All right. So the protocol we're using reuses the 4 to 20 milliamp. All right. Which is nice. This why I have Rosemount here. That's who originally developed it. All right, and it is overall considered open standard, as we talked about. The video talked about the very end. Okay. So anybody can use this. They say, hey, here's the basis. You have to do these minimal things. You have to be able to tell us the 420 signal. You have to tell us this. Blah 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 blah. But if you want to like tweak it slightly, you can do that. All right, and I talked about that little file at the end that had to be able that you had to have to actually decode all the information. So that aspect it is good. All right. And then we talked about FSK, or frequency shift keying, where we are taking data, digital zeros and ones, which is what we've got going on up here, and we are combining that to make with our, what was it, 22,000 was I think one was a 12,000, 1,200, and the 0 was 22. This has that backwards, but I think do I have it down here? Yeah, 1,200 represents 1 and 2,200 represents a 0. All right, so yeah. All right, so that's protocol. It did say this is a pull and response, so the devices don't basically offer anything up unless they're asked for it. All right, so that is definitely very important to know. I guess there is also a burst or broadcast mode. All right. And this is the burst mode. The field device continually transmits process data without the need for the host to send request messages. Although this mode is fairly fast, it cannot be used in multi-drop networks, so it does limit you for what you're able to. I did find it interesting that the video is like, yes, you can have multiple devices, but rarely do you. That was definitely what the video said. Yes, you can, but not often. All right. At that point, you might as well just do any other normal network, as far as I'm concerned. And I believe, just like with all the other networks that we've talked about in this class, that Ethernet is slowly going to replace these until something replaces Ethernet, and then that will slowly replace all the Ethernet devices. This is this lovely world that we live in, right? Technology progresses, and technology, like what? Within a day, it's outdated. All right. You're like, I went out and just bought the newest, highest-end computer, and tomorrow the AMD released something over Intel or whatever. Yep, it lasted one day and now it's outdated. Right. Same thing's going with our industrial network. Every day something new is changing, progressing, getting better, becoming more efficient, whatever the case is. So, but as we said before in this class, the older networks aren't just going to disappear in a day. Like, yes, I am manufacturing stuff on 20-year-old equipment. All right. Next door we have a CNC machine. I believe it's a 99 or a 95. I don't know which one it is. So that is going on 20 plus years old. All right. Depending on which one it is, 24, 24, 29, one of those two. There's a company in town still using that exact same model, producing parts today. So yeah, is it a 20-some-year-old machine? Yes. Does it still work? Yes. So they're like, why replace it? Why spend $40,000 to replace that machine when it's still operating? We can still spend a little bit of money on maintenance each year and keep it operating. There's no point to it. The machine still works. They know how to use it. They know the process for it. They can still get parts and we keep it going. There's no need to replace it. That's the same thing with networks. Until the network stops functioning, they're like, it works just fine. We'll just keep that machine going and we'll upgrade it as we need to. All right. So, but yeah. Anyway, Hart is still there. So, remote options. So we have in conjunction with the 4 to 20 milliamp signal. So it's point-to-point mode. So you have your sensor still sending out 4 to 20 milliamp signals, and then we're gonna get other information outside of that. So that's where we're getting device information and hardware and whatever other stuff. You could do it in conjunction with other multi-field drop stuff. So again, we're doing multiple devices. All right. And you could also do point mode with one field device broadcasting in burst modes, where it's constantly just sending out this information. Like, hey, here you go. Do you care about this? Do you care about this? Do you care? Just constantly talking to you, and you only listening to what you actually. So that is another option. All right. Next comes to the physical layer. All right. So we have our little controller here. So this is what you would actually plug into that network to actually decode the information that's being sent. All right, could you do this on the PLC? Yes, but this is a nice little handheld device that you could add in and still be able to, the PLC would still be able to function. All right. As the video talked about, we do have a multi-master environment. So you could actually have like 4 of these things plugged into one and they will work. All right, now only one master could probably request information at a time. So you all can be like, hey, tell me this. And you'd just be like, well, I got that signal first. Let me respond to that one. All right. So you do need to kind of make sure you're not all trying to access it all instantaneously. All right. So, yep, we could do analog or the frequency shift keying for our communications. This is a 1200 baud rate. All right. So, something to be aware of. Max drop is up to 15 devices. I don't know if the video said that. I don't remember. 15 devices is what we can have on this at once. All right. And that communicator there, that is capable of reading, writing, setting ranges, and calibrating. All right, so it could read information off the Hart device. It could write stuff to it. It can set ranges, and it can calibrate. So it can be like, oh, right now you're actually reading 15 degrees Fahrenheit. There you go. Now you know that. Then the temperature sensor can adjust itself and say, okay, value of this is now 15. So that is very, very helpful. And the other big helpful thing is this can be anywhere on that loop, as long as the impedance is less than 230 ohms. Also, so a little bit of give and take on that one. So we do have lots of commands that communicator can send. We have universal commands, which is dealing with manufacturer and device type, primary variable, units, current output, range, variables, messages, all types of things like that. We have practice commands, which are setting variables, dampening time constant, device range, calibration, self-tests, resets, all sorts of things. And then you've got device specific, which would be like flow cutoff values, start-stop totalizers, density calibration factor, construction information, sensor calibration. So again, a lot going on there. And this is just showing you all those that I just kind of talked about. They're universal. There's the common, and there's the more device specific. All right. And here's the real get the Google for it. What are the benefits? Why would we want to go to Hart? Well, we've got simultaneous analog and digital communication. That's good. We can get a lot more information over those same 2 wires. And now you may be going, that hardware sensor is expensive. Why wouldn't we just replace it with an Ethernet device and run an Ethernet cable and everything? Depending on where you are in your industrial network, running the Ethernet cable might not work. Like, oh, I've got to go through this very small gland hole here, and I got to get 50 feet over that way, and I got to do this, and I got to do that. You might not be able to easily get a new Ethernet cable run, at least while the machine's operating. And then if you do upgrade to something new, now all of a sudden, you have a lot of downtime for getting new equipment set up and all that other stuff. You could like, okay, we can put a Hart sensor in, we're only going to use it for the analog stuff now, and in 4 months, All right, now we want to actually try to use that Hart stuff. Now we just have to replace this one component. We don't have to run any new wires or anything like that. So there is a big benefit of that. We could add more analog devices, although that's not normally the case. Again, multiple masters is a benefit because you could have someone sitting right by the sensor with a communicator plugged in, reading the value instead of having to like plug in the PLC or something like that. So that's nice. This does say long distance communication over telephone line. Okay. Alternative transmission modes, flexible messaging structure. So that's always going to be good. Anytime you can have flexibility with these stuff, that's going to be a huge benefit. So there is a lot of give and take going on. Unluckily, I don't have any good Hart sensors. I don't actually have any good analog sensors. Yeah. It's like, yeah, $100 to $500 is inexpensive. I'm like, not to me. I have a hard time being like, yeah, let me just go buy a few analog Hart sensors. And let me buy a few Hart sensors. Like, there's a whole bunch of things. No, not good. All right. Well, anyway, that would be the end of Hart. Any major questions for me? All right.